Hello everyone, welcome back to AE and PGOE 123. This is assignment 7. In this assignment, we are going to practice to analyze op-amp circuit. Question P.14.9. Determine the closed-loop voltage gain of the circuit shown in figure P14.9, assuming an ideal op-amp. Well, so in this question, we are asked to find the voltage gain of the circuit. Well, the closed-loop voltage gain is A. That is the final output V out, VO here, divided by V in. Well, in this case, V in is an known value, but we don't know V out, and we are gonna find A. Well, so for this question, a typical way to solve this type of problem is to perform node analysis repeatedly. Well, so let's see. We first can perform node analysis here, here, and here. Well, let's see. For point A, for ideal op-amp, V negative is equal to V positive. So here, VA is equal to V positive, that's 0 volt. So we know the value for VA, but in order to find V out, we also need to know other node voltages. For example, the node voltage at point B and C, that's VB and VC. So let's find them. We now have three unknowns. That's VB, VC, and VO. So we need to have three equations to solve three unknowns. And we need to perform nodal analysis. Perform the KCL for 3 times. So let's do that. Well, we first can start to perform nodal analysis at the negative terminal or the inverting terminal of the op-amp. Here, that's at the node A. Assume all the currents leave the node. Because no currents entering the op-amp, so there's the current here is equal to 0, current here is equal to 0. We only have 2 currents at this node, and we assume all the currents leave this node. So the first equation now become VA minus V in divided by R plus VA minus VB divided by R is equal to 0. Here A is equal to 0 because that's equal to the voltage value at the positive terminal. So that this is our first equation. Let's perform a nodal analysis at node B. So we have VB minus VA divided by R plus VB minus 0 divided by R plus VB minus VC divided by R is equal to 0. Similarly, here A is equal to 0 volt. And let's do that again at node C. VC minus VB divided by R plus VC minus 0 divided by R plus VC minus VO divided by R is equal to 0. So now we have 3 equations and the 3 unknowns, that's VB, VC, and VO. 3 equations, 3 unknowns. We can solve this system equation and find that VO is equal to 8 times negative V in. So VO divided by V in, that's the gain A, is equal to negative 8. This is a negative gain because it's connected to the negative terminal of the op-amp, and that's the inverting terminal, you get a negative gain. Question P14.11. Determine the closed-loop voltage gain of the circuit shown in figure P14.11, assuming an ideal op-amp. Well, for this question, again, we need to find the closed-loop voltage gain. That's A, which is V out divided by V in. V in is what we know, but we don't know V out. So let's label this as V out. And here we have a few other nodes, that is VA and VB. Well, VB is also the V negative of the op-amp, and assuming an ideal op-amp, V negative is equal to V plus. Here V plus is connected to the ground, so that's equal to 0 volt, and thus VB is also 0 volt. And now we have two unknowns. We need two equations for our nodal analysis. So we need to perform KCL twice to find these equations. And at node A, let's assume all the currents leave that node. So we have VA minus V in divided by 3R plus VA divided by R plus VA minus VB at 0 divided by 2R is equal to 0. This is our first equation. And we performed our first KCL at node A. So for node another equation we can find is we can perform node analysis at node B. Again, assume all the currents flow away. That's VB minus VA divided by 2R plus VB minus V out divided by 22R is equal to 0. Well, here we can directly write VB at 0 volt and 0 volt. So we have two unknowns, that's VA and V out, and two equations, and we can solve them. We can find that V out is equal to negative 11 V in divided by 5.5, and if we simplify this, we get V out divided by V in is equal to negative 2. P14.19. Analyze the ideal op-amp circuit shown in figure P14.19 to find an expression for V out in terms of VA, VB, and resistance value. So for this question, we are only asked to find V out. We don't need to find it again. So let's see, where is V out? V out is here. And to find V out, we need to see how many nodes we have here. So we have a node here, that's V1. We have another node here, that's V2. We can see that V1 is connected to the positive terminal of the op-amp. So we have V1 is also equal to V plus. And we know that for an ideal op-amp, V plus is equal to V minus, so that's equal to V minus, and V minus is also V2. So V1 is V, and V2 are the same. For this question, we now have two unknowns. So let's say this is V. So our first unknown is V, and the other one is V out. So we have two unknowns. We need to write two KCL equations to perform nodal analysis and solve this question. So let's write the equations. Well, we can first write equations at node 1. Assume all the currents leave that node. So we have V1 minus VA divided by RA plus V1 minus VB divided by RB is equal to 0. Well, similarly, we perform KCL at node 2. That is V2 minus 0 divided by R1 plus V2 minus V out divided by R2 is equal to 0. Well, for the first equation, we can find out that V1 can be written as VA RB plus VB RA over RB plus RA. And for the a second equation, we can see that V out is equal to V2 times R2 over R1 plus 1. Well, V1 is V2, so we can directly substitute in the V1 here. So V out is equal to VA RB plus VB RA over RB plus RA times R2 plus R1 over R1. So that's our V out. Well, for this type of questions that we don't know the exact values, we don't know the numbers for VA, VB, RA, and RB, you can solve. My recommendation is to solve these two equations separately, so it's easier to write the expression for V1 and V out. Then we can combine them together to get the final expression for V out. Question P14.22. For each of the circuits shown in figure P14.22, assume the op-amp is ideal and find the value of V out. Each of the circuit has a negative feedback and a summing point constraint plus. Well, this also means that the op-amp is ideal. And we have 5 questions for P14.22. So let's get started and try question A. We need to find V out. Let's label V out. V out is here. Let's see how many nodes we have. Well, here is the other node we don't know. Let's say that's V negative. Well, we can, for ideal op-amp, we know that V negative is equal to V plus, that is equal to 0, because the V positive is connected to the ground, so that's 0 volt. So here is also 0 volt. Well, for the 2K resistor, we have a voltage drop from V minus to V out. So we have V negative minus V out is equal to V2K. Well, for V2K, we can use Ohm's law to express that. That is 2K times 2 milliamp. The reason the current flows through the 2K resistor is 2 milliamp is that because it's an ideal op-amp, the current here is 0, the current here is 0. So all the current flows provided by the current source flows through the 2K resistor. So here is 2 milliamp. So we have 2 milliamp here times 2K, and this is 4 volt. And we know that this is 0 volt. So VO is equal to negative 4 volt. Question B. Similarly, we need to find V out. V out is here. So let's see how many nodes we have. Well, again, we only don't know V negative. So the only unknown is V negative and V out. Well, we can see that V negative is the same as V plus for an ideal op-amp. And for V plus, we have a voltage source here. So this is 0 volt plus 5 volt is 5 volt. So we have V plus is equal to 5 volt. So now V negative is also equal to 5 volt. Well, similarly, we have a relationship that here V negative minus V out is equal to V3K. That's the voltage drop for the 3K resistor. And now we know V negative and we want to find V out. So our goal is to find V3K. Well, for V3K, similarly we can use the Ohm's law. So that's 3K times the current value. So what's the current value? Well, again, for an ideal PAM, the currents for the two terminals is equal to 0. So all the currents provided by the current source flows through the 3K resistor. So that's 1 milliamp, and this is gonna be 3 volt. So we now can find that we negative is 5 volt and this is 3 volt. So 5 volt minus V out is equal to 3 volt. So V out is equal to 2 volt. Question C. Again, we need to find V out, and V out is the node voltage here. Well, let's see how many nodes we have. Well, we have a node here. Let's say that's V1, and V1 is also the V negative. And we know that for an ideal map, V negative is equal to V plus. V plus is, this is 0 volt, this is 4 volt, so that is 4 volt. So we know that V1 is 4 volt. Well, for an ideal PAM, current does not flow through here. All the currents here are equal to 0. So we have all the currents here flow through here. All the current flows through the 4K resistor, flows to the 3K resistor. Because the current flows through here is equal to 0, so it's actually, you can imagine that there is no branches here. So in that case, the 4K resistor and the 3K resistors are connected in series. So for two resistors connected in series, they have the same current. So we have 0 minus V1 divided by 4K. That's Ohm's law to express the current flows through the 4K resistor is equal to the V1 minus V out divided by 3K. That's the current flows through the 3K resistor. Well, we know that V1 is equal to 4 volt. 4 volt here. So we can easily find that V out is equal to 7 volt. Question 14.22. Again, we need to find the value for V out. Let's see, for the circuit diagram that we have the ohm amp here, and we know that for the ohm amp, for an ideal ohm amp, the current here is equal to 0. So no currents flow through these two terminals, which means that no current flows through the 3K resistors. So this is actually a dead branch. Well, so now let's see that the only current here is the current flows provided by the 3 milliamp current source, because there's no current through here, so all the currents flows like this. Now we also know that V plus is equal to V minus, and V plus is connected to the ground. So the voltage for V plus is equal to 0 volt. So V minus is also equal to 0 volt. Because there's no current flow through the 3K resistor, so there's no voltage drop for the 3K resistor. And thus, because there is no voltage drop, so V out here is exactly the same as V negative. That is 0 volt. So our final answer for V out is 0 volt. Question E. So that's our last question in question P40.22. Again, we need to find V out here. Well, here we know that V plus is equal to V minus is here that is equal to, this is ground 0 volt, it's 3 volt, 0 plus 3, that's 3 volt. So that's 3 volt here. So V plus is equal to 3 volt. So we have V minus is also equal to 3 volt. And here we can see that this is the positive terminal higher. So we have V out plus 2 volt is equal to 3 volt. and we can directly find V out is equal to 1 volt. Question P14.25. Analyze each of the ideal op-amp circuit shown in figure P14.25. Find the expressions for I/O. And we are also asked to find what's the value of the output impedance for each of these circuits. The impedance is the same as resistance in this case. And why? Well, so we need to find the I/O. I/O is current here. That's the current flows through the load. Well, let's see. We have I/O flows through here because these two are ideal op-amp. No currents here, no currents here, and no currents here, no currents here. Well, so we can see that if there's no current here and here, the only way the current flows is through this route. Thus, we have, let's say, at this node, the voltage is V minus because that's connected to the negative terminal here, and here, let's say that's V minus 2. Because it is connected to the terminal here. And we know that because V plus is equal to V minus for an ideal op-amp, so here they are both equal to V1 for the upper op-amp, so that's equal to V1. And similarly here, V2 negative is also equal to V2. Well, because I/O is the current here and also here, so I/O is, according to Ohm's law, that's V1 minus V2 minus divided by R. And we can also write them as V1 minus V2 divided by R if we substitute in the numbers here. Substitute in the numbers here. So I/O is V1 minus V2 divided by R. And we can see that this expression is dependent of the output impedance. We can see there is no the resistance for the load involved in this expression. So we can see that the output impedance is infinite. Well, question B. Similarly, we need to find I/O. I/O is here. We can see that we have two op-amps here, but the analysis techniques is the same. The basics are the same. So we have for this op-amp, because it's an ideal op-amp, there's no currents flow through here and here. So the only currents that leads to I/O is the currents here. This is also I/O. That's the current that flows to the resistor RF. But how can we know the I/O? We can perform the Ohm's law for the resistor RF here. But we first need to know the node voltages for these two nodes. Well, let's see how many nodes do we have. Well, we have nodes here. Let's say that's node A, and node here, and node B. We also have node here, node D, and here node C. And finally here, node E. Well, to find the I/O, we need to use node D and E. So that's I/O is equal to VD minus VE divided by RF. Well, for the first op-amp, let's say that's op-amp 1 and this is op-amp 2. For op-amp 1, because for node A and B, they are connected to V minus and V plus respectively. So we have VA is equal to V minus and is equal to V plus. That's also equal to VB. so they have the same value. And similarly here for C and E, they are connected to the negative and positive terminals respectively. So VC is equal to V minus equal to V plus and is also equal to VE. Well, so now we know that these two have the same value, and these two have the same value. Well, so we now only have 3 unknowns. So we can find 3 equations to solve this problem. And well, similar to the previous questions, we can perform nodal analysis. So let's first do it at node A. Well, now we can find that Vin is not connected to the ground, so that's a floating source. Well, in that case, we also need to label the node voltages for the node here. This is V1 and then this is V2. We have V1 is equal to V2 plus Vin. And we can first write the KCL equation for node A. So we have assume all the currents leave that node. So we have VA minus V1 divided by R plus VA minus VD divided by R is equal to 0. Similarly for node B, no currents here. So we have VB minus V2 divided by R plus VB minus VC divided by R is equal to 0. If you simplify the first equation, you have 2VA minus V1 minus VD is equal to 0. And simplify the second equation, you have 2VB minus V2 minus VE is equal to 0. And let's say this is 1 and this is 2. If you have 1 minus 2, that is 2VB minus 2VA plus V1 minus V2 plus VD minus VE is equal to 0. The reason why we do this is because we don't know V1 and V2, only know its relationship is here. So now we can have, from this equation, we know that V1 minus V2 is equal to Vin. So we can substitute the value of V1 minus V2 as Vin here. Well, we also know that VA is equal to VB, so let's cancel it out. So the only relationship we left with is Vin plus Vd minus Ve is equal to 0. Well, now we get a relationship between Vd and Vin, Vd and Ve. Well, because our goal is to find I/O, and I/O is exactly the Vd minus Ve over Rf. So from here we get Vd minus Ve is equal to, move Vin to the other side. So we have, this is minus Vin, so this is minus Vin over Rf. So this is our final result.